Chapter 1 dealt with data, the different types of data. Chapter 2 dealt with presentation forms, different ways that you can present data, graphical forms and tabular forms. This chapter deals with numerical measures, different things that you can calculate to help you describe a set of data. Now, this particular presentation, or this video, we're going to go through measures of location. I'm going to break it up and use a different video to talk about measures of variability. We're going to cover the mean, the median, the mode, the weighted mean. We're not going to cover the geometric mean. There are some uses for that one, but they're not really that common. So we're going to omit the coverage of the geometric mean. All of those, the mean, the median, the mode, the weighted mean, all those are measures of central tendency. Percentiles and quartiles are measures that are still location measures, but they're off of the center. Now, when you calculate measures from a sample, they're referred to as statistics. When you calculate measures from a population, they're referred to as parameters. The big difference between the two is the symbol that you use. We use a lowercase n for the number of items in the sample, and we use an uppercase N for the number of items in the population. The idea in statistical inference is you want to look at a small subset of a large population and be able to use these measures in order to make inferences about the larger group. The sample statistic that you calculate is called a point estimator of that population parameter that you're trying to estimate. Now, the mean, or what's commonly referred to as an average, is the one that's used most prevalently. It's a measure of central location. We're also going to cover the median. We're also going to cover the mode. But it's the simple average. There are different types of averages. The mean that we're going to be using is referred to as the arithmetic mean. We use the symbol x with the dash over the top of it, and I'm going to say x bar when I refer to that one. It's the point estimator of the population mean, and we use the Greek letter mu as a symbol of the population mean. But we're going to calculate sample means in order to estimate population means, but we won't get to that until we get into chapter 8. Now, in terms of the notation, in order to calculate x bar, the sample mean, you take the sum of the values in your sample and then divide it by the sample size. The capital sigma is a summation notation. So when you see the capital sigma, what you want to do is to think, add them all up. In this particular formula, there's a subscript of I, but it really doesn't make it clear what the I stands for. In a later slide, I'm going to explain what the meaning of that is. Now, the population mean, we use the Greek letter mu to represent the population mean. You take the sum of all the values and then divide by the number of values in the population. But it's essentially the same formula. We're just using different symbols. Now, the example that they had inside these PowerPoint slides dealt with apartment rents. They had 70 apartment rents, and they used these numbers to illustrate the different concepts. But this is really too large a data set for me to explain the different properties about the sample mean. So I'm going to use a smaller size data set to explain what the properties are. The smaller sample, it's the number of years that a company was in business. One of the companies in the sample was in business for 10 years. One of them was in business for 15 years. There were a couple of them that were in there for 3 years. X bar is a sample mean, And in this formula in the middle of the slide, you can see the I starts at 1 and it goes all the way up to n. So the x sub I, the I is an index that you begin with 1. So you have x with a subscript of 1, which is the first value in your set of data. And then the summation says that you're going to do addition. You're going to add these numbers together. So you take x sub 1 and then you add x sub 2 and you add x sub 3 and you add the fourth one and the fifth one and so on until you add up all of them. So you can take this notation that's here in the middle and replace x sub 1 with the 10, replace x sub 2 with the 6, replace x sub 3 with a 14. The seventh value is a 3. But all the mean is that you add up all the numbers and then divide by the number of values. But the notation that I tend to use, I just use the capital sigma and I don't bother with the subscript. When you see the capital sigma, that just means add them up, add all of them up. So here, if you add up the 7 numbers, you get a sum of 73. You divide that by 7 and you get a 9. So the sample mean, or the average, is calculated as 9. So we take and add up the numbers and figure out that the mean is 9. Now that's a point of central tendency. But in what sense is the 9 in the middle? Well, where it has that middle property is the way that you look at the deviation from the mean. You take the difference between the number and the mean. Now if a number is bigger, if it's larger than the mean, you're going to get a positive deviation. If a number is less than, if it's smaller than the mean, then you're going to get a negative deviation. And by looking at the deviations, that's where you get the property that you get balance with respect to the mean. Now the next slide shows a dot plot, and it shows, at least I'm trying to show it visually, what we mean when we say that the mean is the balancing point of a set of data. Now when I click on the slide, it should show kind of a teeter-totter effect. Let's see if this is going to work. But the mean is at 9. When you look at the 2 3s that are in the data set, when you figure the deviation from the mean, 3 minus the 9 is a negative 6. But there are 2 of these, so you get 2 negative 6 values for deviations. The 6 is only 3 units below the 9, so you get negative 3 for the deviation. There are 4 values in the data set that are above the mean. The 10 gives you a positive deviation of 1. The 12 gives you a positive deviation of 3. The 14 is 5 above the mean. And the 15 is 6 above the mean. Now when you add up all the positive deviations, we get 15. And that exactly balances the deviations for the 3 numbers that are below the mean. And this is always going to happen. When you add up all the numbers in a set of data and divide by the number of values, you're always going to come up with a number where the deviations from the point in that data set, that they're going to balance each other. But the sum of the deviations from the mean is always going to equal 0. So the concept of the mean, what makes it in the middle, has to do with the deviations from the mean. And this implies something important about the use of the mean as a measure. You need to have at least interval level data. If the difference between 2 values is not well defined, it really doesn't make any sense to calculate the mean as a measure. If you have nominal level data, or if you have ordinal level data, it really doesn't make sense to figure out what the mean is. Now we're going to go back and look at the apartment rents example and look at the mean, and we're also going to look at a couple of other measures of central tendency. Now here the apartment rents have been sorted. 525 was the smallest value. 530, there's a couple of those. 535, there were several of those values. But they've been sorted. The first one's up at the top, and as you go left to right, and from the top to the bottom, you can see the numbers are in sequence. When you add up these 70 values, you get 41,356. And then you divide by 70, and the mean, or the average value, is 590.8. Now that's in the middle in the sense that the deviations, when you take the difference between 525 and 590.8, and you do that for all the numbers, if you add all those up, you're going to get 0. But that's the way that this number is in the middle. The median is in the middle in the sense that half of the values are less than or equal to the median, and half of the values are greater than or equal to the median. So to find the number in the middle, we have 70 of them. So there'll be 35 numbers that are below the median, and then we're going to have 35 numbers that are above the median. But the median is halfway between the two values in the middle. There's an even number. If there's an odd number of values, then there's going to be a number in the middle when you put them in order. But when there's an even number, the convention to come up with the median is just to take the average of the two numbers that are in the middle. So 575 plus 575 divided by 2 would give you 575. But the property, what puts it in the middle, is that half of the values are less than or equal to it, and half of the values are greater than or equal to it. Now the mode is in the middle in a probabilistic sense. If you just randomly selected one value from this set of data, which one would you most likely obtain? Well, it's going to be the one that occurs most frequently. And in this data set, that's the 550. So the mode is 550. Now Excel has functions built into it that will calculate these measures very efficiently. The average function will calculate the mean for you. All you have to do is put in the range of the data values. There's a median function that will calculate the median. It's not necessary for you to go through there and pre-sort the data. It'll do the sort process for you, and it just figures out what the median is. There's also a couple of different mode functions. The .sngl is the single mode. It's going to provide you with a single number. That's the mode. It's probably going to give you an error if it turns out that there's more than one value that occurs most frequently. Now percentiles, this is a way that you can figure out location percentages of the data values that are smaller than some number. There are also quartiles when you break the data set up into 4 pieces. But we can figure out what's the value such that 25% of the data is less than or equal to this. What's the value such that 75% of the data is less than or equal to this. But you can get things other than 50%. 50% of the data is less than or equal to the median. But 25% of the data is less than or equal to the first quartile. 75% of the data is less than or equal to the third quartile. And what this formula does is it calculates the position, the location of a particular percentile. You take n plus 1, divide it by 100, and then multiply it times the percentile that you want. Now there's a slide in here that calculates the 80th percentile. So if you want to do this, when you plug it into the formula, you're going to plug in 80 for P. So we're going to get the n plus 1 over 100, and then it's going to be multiplied times 80. Now the way this formula is actually written, you would take the 80 and divide it by 100 and then multiply that times n plus 1. But I think it's easier to remember it if you think about, I want to take this data set and I want to break it into 100 pieces. So I take n plus 1 and divide it by 100, and that tells me the location of that first percentile. So if I want the 80th percentile, I'm just going to multiply that number times 80. So when we do the calculation here, we come up with 56.8. So when you put the numbers in order, there's going to be a number at location 56. There's going to be a number at location 57. And what we want to do is to figure out what the value is that's 80% of the way between those two numbers. So here's our set of apartment rents, and they're sorted. We're looking for number 56.8. So the first 10 values, the smallest 10 values, are in the first row. Then we get to number 20, we get to number 30, to number 40, to number 50, and then the 670 is the one that's in the 60th position. So we can back up from that point, get to number 59, number 58, 57 is 649, and the one in position 56 is 635. Now we want to go 80% of the way between these two numbers. So you take the difference between 649 and 635 and multiply that times 0.8. And then whatever that number is, that's what you add to 635. And you're going to get 80% of the way between these two. And that number turns out to be 646.2. So 646.2 relative to this data set is the 80th percentile. 80% of these numbers are less than or equal to 646.2. Now since 80% of them are below it, 20% of them are above it. So 20% of the values are greater than or equal to 646.2. And that's what's illustrated on this slide. But that breaking point right there is where the 80th percentile is. It's 80% of the way between the one in location 56 and the one in location 57. Now you can come up with quartiles by using the fact that 25% is equal to a quarter. The second quartile, which would also be the 50th percentile, is where you're going to have the median. 50% of the values are less than or equal to it, so 50% of the values are greater than or equal to it. And when you want the third quartile, you just use 75%. So you'd have 75 times n plus 1 over 100, and that would give you the location. And then once you have the data in sorted order, you can figure out what the value is at that location. So here we're finding the third quartile. We're finding the 75th percentile. So we plug the number into the formula and we figure out that it's located at position 53.25. Now in this case we're lucky. The 10th one, 20th one, 30th one, 40th one, 50th one. 610's in position 51. 615's in position 52. But the numbers at location 53 and 54 are the same. So if I go 25% of the way between two numbers that are the same, I'm just going to get that same number. So the value of the third quartile for this particular set of data is 625. That concludes the coverage of the different location measures. Now we covered the mean, the median, and the mode for central tendency. And then the percentiles, you can also generate quartiles from those, are for values that are not in the middle. You can get non-central tendency measures by using those. The next video, the next PowerPoint presentation, is going to deal with measures of variability. And we'll talk more about that later.